of times I give you the homework at the end of the chapter, I wanted to separate it to permutations, combinations, and then probabilities. Because you need to see the difference not only between a combination and a permutation, but when they ask you how many ways versus what is the probability of. Because too many kids will just do the ways and never give me a probability. So I'm going to spend a day on just putting it all together with probabilities. So you did number 7, which can everybody put these in their calculator? 9p5, 9 things taken 5 at a time. And again, you start with your 9, you give me 5 lines, if you like to do it this way, and you multiply. Okay, whichever way you prefer to do this is good for me. And we jump down to 15. Okay, put my things off. So number 15. Now, the difference between number 15 and number 16 is what I really want you to notice. The number of ways 8 cars can line up in a row for a car wash. They don't say that order matters, but when you make a line, doesn't it matter who comes first, who comes second, who comes third? So when you line up, order matters. So that's a permutation. You didn't have to work it out, you just had to say permutation combination. Versus number 16, where it says the number of ways. Notice they both start off with the number of ways to form a 4-member committee from 10 people. Committee, which should be O, not 0. Committee is my key thing here. Order does not matter in this one. So that's my combination. So can you spot the difference between a combination and a permutation by the way they word this? Remember, they're not going to tell you order matters, order doesn't matter. If you see things that line up in a row, I got order here. Committees, order does not matter. Think of what you do when you're on a committee. The starting lineup for a softball team consists of 10 players. How many different batting orders, starting lineups can you have? We have 10 girls. You could even make 10 lines. This works all the time. Once you start this, you will probably realize, oops, 10 factorial, all the way down. There's your 10 factorial, or your 10 things taken 10 at a time. And that's a large amount of a lot of ways that you can line up 10 people. So feel bad for your coaches when they have to make the lineups. Number 23, there are 50 runners in a race. How many ways can they finish first, second, third? Lay out your lines. This is your first, your second, your third. 50 of any of the 50 can finish first, but the one that finished first can't finish second or third. So there's your 50 times 49 times 48. If you can, set it up in a permutation. Sometimes it's easy to lay out the lines first and then work your way into a permutation. Or if you read it this way, 50 people taken 3 at a time, 3 places, there's your permutation. Everybody okay with these? Okay. It's when we throw the probabilities. Permutations, combinations, when we do them separately, they're okay. When we throw probabilities, they start to get a little trickier. Read your question? No? They get a little trickier. So I wanted to get down pat to how many ways we're doing. Your archaeology club, 38 members. How many different ways can you select a president, a vice president, a treasurer, and a secretary? 4 positions. 38, 37, 36, 35. Oops. 38 things taken 4 at a time. There it is. It's a lot of different ways for 38 members to select 4 positions. Remember, order matters in this. You'd rather be the president than the vice president. Order matters. You are putting together 4 spacers, 10 gold charms, 8 silver charms on a bracelet. In how many distinguishable ways can the spacers and the charms be placed on the bracelet? So what they're saying is, it doesn't matter to me if it's one gold charm or which gold charm it is. It's still a gold charm versus a silver charm versus a spacer. They're distinguishable ways. Distinguishable means you have to take out your duplicates. So this is the same as your trees, your 5 maples, your 4 poplars, whatever we did yesterday. So add up your total, that goes on top, and take out your duplicates. 4 factorial for spacers, 10 factorials for gold charms, 8 factorial for silver charms. Now when you put this in your calculator, notice what happens. 22 factorial divided by 4 factorial, 10 factorial, 8 factorial. Order of operations says left to right, divide or multiply. I'm going to hit this divide right here. And then I'm going to multiply it by this, multiply it by this. So you have to have parentheses around that denominator. You want it to go to your denominator first and then divide. Okay, so be careful. You can't put it in your calculator, then divide. You got to work it this way. That was it for you. Permutations. Are we good with this part? Questions? No? All right. Today I want to hit, now, just like the permutations, your book does it differently than I do. Your permutations, for instance, 10 things taken 2 at a time. Your permutation says subtract them and divide by the difference so that you get rid of them. I don't do it that way. I say go 10 things 2 at a time. 10 times 9. Okay? Now, your combinations, they also do things a little differently. 10 things 2 at a time. They say this. 10 factorial over 10 minus 2 factorial, which is 8 factorial. Excuse me. And then 2 factorial. What this does is, you can visualize this. I'll write it out. It takes out from 8 on down. Do we take it out? So it technically goes 2 positions down, like we did our permutations, but then it divides by whatever the R factorial is. See it? Because the other ones cancel each other out. So if you're going to do these by hand, go 2 positions down, just like you did your permutations, and here's where your combinations come in. You take out the duplicates. That's this factorial, 2 times 1. And this is why you can do a lot of these in your head. So this will give us 45 ways to do this. Okay? I mean, you can absolutely use your calculator. You have to put in your 10, go to math, go to probability, go to the C, NCR, and then put in your 2. But I want you to see what it's doing. And this is a good way to show the difference between a permutation and a combination. My way. 10 times 9 is your permutation. The combination says divided by the duplicates. Take this out. 2 times whatever that R is. If it's 4, it's 4 times 3 times 2 times 1. Whatever that grouping is. And can you use your calculator? Absolutely. The factorial is under math, probability, number 4 maybe? The exclamation mark. I think it's the P is 2, C is 3, I think the exclamation is 4. Okay. Alright. Example 5. A State Department of Transportation plans to develop a new section of interstate highway and receives 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different, and look, they use the word different combinations of 4 companies can be selected from the 16 bidding companies. So the first thing you say to yourself, does order matter? It doesn't matter. If it's no, then it's combinations. If it's yes, then it's permutations. This is the biggest difference right here. So we say order does not matter. What word gives it away? Well, they ask for different combinations. A lot of times they say committees, groups, subgroups, but this one said combinations. So as soon as you determine combinations, C. You determine permutations, P. So we know this is a C. How many total do we have to choose from? 16. That's your N. Looking at 16 of them. How many do I want to choose?
4.
4. That goes here. And if you do it my way, 16 things 4 at a time. And then 4, 3, 2, 1. And you can combine a lot of these. Like 3 goes into this 5 times. You have to do this by hand. This is 8. It comes out of here twice. So that's a little bit more doable than if you didn't have a calculator. I definitely don't use their way because it's too long. So your main difference that I want you to see is, am I using a combination or am I using a permutation? Yeah, I want you guys to try it yourself, number 5. Put something right here.
Yeah.
So, does order matter? What word? Committee. Good. Well, how many committees? So, order does not matter. That's what you determine first. So, therefore, you know this is a C. How many do you have to choose from? How many employees do you have to choose from? 20. And how many do you want? 3. Now, if you put this in your calculator, or if you do it the long way, 20 times 19 times 18 over 3 times 2 times 1, this is 6, and it goes in here 3 times. It makes it doable. And I was just saying to Felicia, like maybe you didn't have a graphing calculator, you just had a regular calculator, and you didn't have the C and the P on it. It makes it doable for you. Also, be careful. If you switch these around, your calculator doesn't give you an error. It gives you a 0. So it doesn't say syntax error, it just says 0. Because you can't do it, you get 0 ways to do this. So you be careful what order you put these in. Now, I'm giving you a group of things to do first. But I want to take a look at number 35. This is a great example of your how many ways when you do this, when you change the rules a little bit. So on page 175, look at number 35. A restaurant offers a dinner special that lets you choose from 10 entrees, 8 side dishes, and 6 desserts. 13 desserts. I'm sorry, I read the line underneath it. 13 desserts. Now, it says, the lesson, you can choose 1 entree, 1 side dish, and 2 desserts. My favorite kind of deal. But it used to be you could choose 1 entree, 1 side dish, and 1 dessert. And what's that called? When we do what principle is that called? No? When we figured out how many different ways you could make your combinations of your meals that way. I wear 3 pairs of pants, 2 shirts, 5 sneakers. How many different outfits can I make? What do we do with those? We multiply them, right? What's that called? The counting principle. So our counting principle, I want you to stay with me for a minute. Our counting principle would say this. How many ways can we make dinners out of this? 10 times 8 times 13. Choosing 1 of each one, right? Will give us how many different dinners, combinations can we make. Now, the problem is this. You can choose 2 desserts out of 13. So how do I represent just that piece? choosing any two desserts out of 13. Choose. No. Does it matter what order I choose my desserts? So is it a C or a P? C. How many do I have to choose from? How many do I want? And this part stays the same. Yeah, this was a little bit of a thinker. Do you see it? Your counting principle says, like, you know, the ice cream. I have 5 different ice creams, 4 different toppings, 3 different syrups. You know, 10 times 4 times 3. 5 times 4 times 3. It's the same as this one. 1 entree, 1 side dish, 1 dessert. 10 times 8 times 13. However, this time they said any 2 desserts. Does it matter what order I choose them in? No. But the rest of it stays the same. 10 times 8 times the combination part. Yes.
If you were to do 31 choose 4, would that be wrong?
Yes. You don't add them up. Because what it's asking you at the end is how many different ways can you make a meal using one of these, and 2 of these. It's a lot of different ways you can make a meal. So you go to these places and it takes you a very long time to decide.